Welcome folks, a video on advanced applications of integrals. In this video, we're going to be discussing separable differential equations. So we'll start off by discussing how to classify a differential equation as separable. We'll talk about a strategy for solving those equations, and then we'll solve a couple initial value problems. Recall here we're discussing first order separable differential equations, so the highest derivative you see is a first derivative. So if such a first order differential equation is separable, if it can be written of the form dy dx equals f of y times g of x. So this is where the term separable comes from, that the right-hand side separates into a product, a pure function of the independent variable, in this case that independent variable is x, and a pure function of the unknown function. The unknown function here is y. So here's an example. This differential equation, dy dx equals sine of y times x times e to the x plus 2y, turns out to be separable. And to see that, we can formally separate and express the right-hand side here as f of y times g of x. Using properties of the exponent, we can see that e to the x plus 2y separates as e to the x times e to the 2y. And then I'm just formally collecting up these terms, e to the 2y sine y and x e to the x. So we can see that this differential equation can be written as dy dx equals f of y times g of x, with f of y and g of x chosen carefully. Okay, it turns out any separable equation can be solved maybe by formally separating variables and integrating with respect to, sorry about that typo, x. So here's what I mean by that. We can separate variables by moving the f of y here to the left-hand side of the equation and rewriting the equation as 1 over f of y dy dx equals g of x. We can then integrate both sides with respect to x here, and we see that the integral of the left-hand side should be equal to the integral of the right-hand side. Now, in sort of a cool twist, this dy dx times dx is actually just, by the chain rule, equal to dy. So let's see an example. Before an example, I'll mention that separation of variables typically yields what we'll call a one-parameter family of implicit solutions. So there are a lot of words here. The one-parameter part comes from a constant of integration, and a family of implicit solutions means that we haven't solved explicitly for the unknown function. As we'll see a little while later, what we'd like to see is an explicit solution, and sometimes you have to be a little bit careful checking out the explicit solution. So here's an example. Let's go ahead and find a one-parameter family of implicit solutions to this separable differential equation. So we can see that this is separable by writing the right-hand side as f of y times g of x. So here we see the strategy that we outlined on the previous slide. We're going to separate formally by expressing the differential equation as y times dy dx equals x. And then we can integrate both sides with respect to x. Y dy dx and integrated with respect to x is equal to x integrated with respect to x. Now again, this twist here is chain rule, and the chain rule tells us that this product, dy dx dx, is really just dx. And I misspoke there. The product dy dx dx is actually dy by the chain rule. So integrating y dy is the same as integrating x dx, and we can express our implicit family of solutions as 1/2 y squared equals 1/2 x squared plus c. Okay, and again here we see an illustration of those two words, implicit, not explicitly a function of y as a function of x, and family, right? So this is a solution for any c. Okay, it turns out that that little chain rule trick always works. And in practice, what you do is sort of just separate all the y's and all the x's and then integrate both sides. Here's what I mean by that. Okay, so what's really happening here again is that dy dx dx is equal to dy by the chain rule. In practice, what happens is that we sort of we think of moving this differential dx over to this side and moving this f of y over to that side and expressing our separated differential equation here as 1 over f of y dy equals the integral of g of x dx. Now, technically, what's not happening is we're not separating the fraction representing the derivative into numerator and denominator. It's not really a fraction, right? It's just fractional notation for a derivative, but in practice, that's how it works out. So you can sort of think of it that way. Okay, let's talk about initial value problems. We saw previously that an initial value problem is a differential equation together with an initial condition. So in practice, to solve an initial value problem with a separable first order equation, we first find that one parameter family of implicit solutions like we talked about before. Then we'll choose one member of that family to satisfy the initial value if we can. And if possible, we'll solve for the explicit solution. So in this case, that unknown function y is a function of x. So we'd like to write y as a function of x. Okay, let's go ahead and see an example here. Let's solve the initial value problem. Dy dx equals x over y, where y of 2 is equal to 1. Now, this is a differential equation that we saw previously, and we previously found an implicit family of solutions to this differential equation. So that implicit family of solutions was 1/2 y squared is 1/2 x squared plus an arbitrary constant. If y is 1 when x is 2, it must be that 1/2 times 1 squared is 1/2 times 2 squared plus a constant. And that allows us again to solve for our constant. Solving that algebraic equation for c, we see that c is -3/2. Substituting that back into the implicit family of solutions, we see that y squared is equal to x squared minus 3. And we can choose the positive square root here because we know we want our y value to be positive. So we choose y equal to the square root of x squared minus 3. This is an explicit solution to the initial value problem. Now, if we had a different initial condition, we may have had to be a little more careful with our solution. So what happens if y of 2 is -1 instead? Well, let's go ahead and check it out. We use the same implicit family of solutions. 1/2 y squared is 1/2 x squared plus a constant. And if y is -1 when x is 2, then it has to be, again, that c is equal to -3/2. We can plug that into our implicit family of solutions and solve for the explicit solution. In this case, however, when we go to solve for our explicit solution, we have to choose the negative square root in order to ensure that our solution is negative at x equals 2. So the explicit solution to the initial value problem in this case, y as a function of x, is y equals minus the square root of the quantity x squared minus 3. Okay, let's do one more example. Here's one more example. Let's solve the initial value problem. Dy dx equals, dy dx plus 3y equals 210. Now, initially, this doesn't look exactly like an initial value it doesn't look exactly like a separable differential equation, but we'll go ahead and rewrite it so it does. So manipulating the equation algebraically, moving the 3y to the other side, we can see that we can express our differential equation as dy dx equals -3 times y minus 70. So here's our form, f of y times g of x, where f of y is y minus 70, and g of x is just the constant -3. So we'll go ahead and formally separate variables and integrate both sides to look for an implicit family of solutions. So when we separate variables and integrate both sides, we see our implicit family of solutions. It's right here. Natural log of the quantity y minus 70 in absolute value is equal to minus 3x plus an arbitrary constant. And here I've written that arbitrary constant as plus k. It doesn't really matter, but you'll see why I did that in just a moment. Now, when we go to solve for our explicit solution, we can see that we want y minus 70 to be positive in order to get y of 0 equal to 100. So we'll take the positive absolute value here. Using that inverse relationship between the logarithm and the exponential, we see that y minus 70 has to be equal to e to the minus 3x times e to the k. And of course, when k is a constant, e to the k is 2. So I'm just going to call that constant c. So here is our explicit family of solutions, y equals 70 plus c times e to the 3x. Now, in order to satisfy our initial condition, all we need is for y to be 100 when x is equal to 0, and we can see that c equals 70 does the trick. Sorry, c equals 30 does the trick. So here's that computation ensuring that we satisfy the initial condition. 100 equals 70 plus c times e to the 0. And again, this tells us that c equals 30, giving us our solution to the initial value problem. Y of x is 70 plus 30 times e to the minus 3x. Okay, folks, hope you've enjoyed this quick introduction to separable first order differential equations. Have a great day, and we'll see you next time. Bye-bye.